Chinese researchers found something surprising in the dust brought back by the Chang'e-5 mission. Thin layers of carbon called graphene. The spectral fingerprint matched multi-layer graphene, a carbon lattice stacked 2 to 10 atoms thick. Lead author Wei Zhang of Jilin University says the find could reshape ideas about lunar birth and guide resource plans for future crews. The study marks the first confirmation of natural few-layer graphene in lunar material, opening new questions about how carbon behaves on airless planetary surfaces. Apollo samples didn't show much carbon, so scientists long believed the moon was dry and formed from a violent crash with early Earth. But that idea started to change in 2020, when Japan's Kaguya spacecraft found carbon leaking from nearly every part of the moon's surface. Carbon shapes volcanic chemistry and potential fuels, so confirming its presence changes both academic debates and mission planning. Lunar engineers drafted oxygen plants that would discard carbon, but richer soil chemistry invites factories that turn it into plastics or life support gases. Carbon fingerprints help trace a body's origin, because the element vaporizes in hot impacts, yet survives calmer accretion. Finding it preserved narrows the temperature range and timeline that must have shaped the young moon. Chang'e-5 collected about 3.8 pounds of moon dirt from a region called Oceanus Procellarum. Back on Earth, Zhang's team examined a tiny grain using a special laser that doesn't damage the material. The results showed clear signs of well-formed carbon layers, with patterns that matched what scientists expect from high-quality graphene. A faint signal also suggested the layers were mostly free of damage or flaws. The laser analysis revealed a faint D band, along with strong G and 2D bands, a pattern that points to high-quality carbon layers arranged in a graphite-like structure. Detailed images taken at very high magnification confirmed that the material contains stacks of 2 to 7 thin layers, spaced about 0.35 nanometers apart, just like the graphite found on Earth. Iron-bearing nanoparticles nestled beside each stack, a clue that metallic catalysts helped assemble the carbon during short heating events. Similar core shell structures have appeared in meteorites, reinforcing the catalytic path. The moon lacks a thick atmosphere, and its soil has constant solar wind protons racing about 250 miles per second. Those ions break bonds, sputter atoms free, and can spark plasma flashes that momentarily heat dust above 2,000 F. Zhang's team that carbon gases, carried by solar wind, stuck to hot, iron-rich dust and slowly formed layers of graphene. Ancient volcanic eruptions in the area might have kept things hot long enough to create thicker coatings. Laboratory work shows graphene can grow on iron at temperatures as low as 752 degrees Fahrenheit, matching those lunar conditions. The paper explained that the way these minerals helped form natural graphene could lead to new, affordable methods for producing high-quality graphene on a larger scale. The presence of nitrogen, sulfur, and molybdenum in the same grains hints at complex chemical traffic rather than a single impact flash. That mosaic may preserve a timeline of multiple events, waiting to be teased out grain by grain. The classic giant impact hypothesis is a Mars-sized body struck Earth about 4.51 billion years ago, ejecting mantle rock that later cooled into a carbon-poor moon. Graphene inside young Mare basalt weakens the carbon-poor part of that story, because indigenous sources must have survived or accumulated long after any fiery birth. One alternative envisions a slow buildup of dust within Earth's orbit, which would naturally trap carbon. Another keeps the giant impact, but suggests the resulting vapor later reaccreted solar wind carbon during a drawn-out magma ocean phase. The authors remark that their findings suggest that the moon may still be capturing carbon, which could change how scientists understand its makeup and history. Future missions that collect deeper samples could help determine if this process happens only on the surface or throughout the moon. Graphene stands out for its strength and electrical prowess, so prospectors see value in harvesting it alongside oxygen, pulled from molten regolith. Sheets only a few atoms thick could reinforce radiation shields, line supercapacitor electrodes, or filter water inside early lunar habitats. Because the material occurs with iron, extraction schemes might combine magnetic separation with gentle sonication to peel off the flakes, without hauling fragile gear from Earth. Making the material directly on the Moon could avoid the high cost and challenges of sending carbon nanotubes or plastics all the way from Earth. Let's pause for a few seconds and give me a like for this video. Thank you so much. Chang'e's group plans to probe mechanical and thermal properties of the natural sheets to judge whether they rival lab-grown analogs. Each additional data point will feed the growing push for a multinational sample return program that maps carbon in 3 dimensions. A new study by Chinese scientists on lunar samples collected by the Chang'e-6 mission from the far side of the Moon has unveiled a startling discovery about the lunar mantle's reduced state. This finding not only provides new insights into the Moon's internal composition and evolution, but also highlights a significant difference between the near and far sides of the Moon. The study, published in the journal Nature Communications, details how basalt samples from the Chang'e-6 landing site originated from a lunar mantle that is not only drier and more barren, but also more reduced than its near-side counterpart. The word reduced refers to a state where elements are in a very low oxidation state, suggesting the mantle material is either more primitive or was reduced by a major impact event. According to Yang Wei, a researcher at the Chinese Academy of Sciences Institute of Geology and Geophysics, this discovery challenges previous assumptions. The redox state of a planet is a key indicator for understanding its internal processes and surface habitability, Yang explained. At least these results prove that hundreds of kilometers deep, the near and far sides of the Moon are still different. This is our new discovery. The scientific significance of the Chang'e-6 mission extends beyond geological analysis. China's lunar exploration program is shifting from geological studies to engineering applications, such as in-situ resource utilization and lunar soil brick manufacturing. These studies will support future missions, including crewed moon landings and the construction of a lunar research station. In a show of commitment to international scientific cooperation, China has shared lunar samples with the global community. To date, the China National Space Administration has distributed 9 batches of lunar research samples, totaling 125.42 grams. This includes 2.18 grams of Chang'e-5 samples, provided to 7 institutions in 6 countries other than China. Scientists worldwide have already published over 150 research papers based on these samples, underscoring the international impact of China's lunar exploration missions. Samples that peel back layers of lunar mystery, like an archaeologist unearthing forgotten civilizations. These basalts, forged in volcanic fires 2.8 billion years ago, whisper tales of a moon once alive with molten fury, its magnetic shield flickering erratically against the cosmic void. Imagine the far side, that hidden face we've romanticized, as eternally silent, scarred by colossal asteroid strikes that reshaped its mantle, depleting it of volatiles like water, potassium, and thorium, leaving it drier and more barren than the near side we know so well. This asymmetry isn't just geological trivia. It's a poignant reminder of the Moon's brutal infancy, a survivor of cataclysms that could have extinguished its inner fire. Yet here it stands, resilient and revealing. Delving deeper, these samples confirm the ancient global magma ocean, a seething sea of liquid rock enveloping the young moon, cooling unevenly to birth its dichotomous hemispheres. The far side's super-reduced state, with elements locked in low oxidation forms, hints at primitive origins or massive impacts that stripped away oxidizing agents, challenging our core narratives of lunar birth. And the carbon story evolves. Building on Chang'e-5's graphene, new analyses suggest ongoing solar wind implantation, potentially enriching deeper layers with this wonder material. Picture it, lunar regolith not as dust, but as a treasure trove, where iron nanoparticles catalyze graphene formation amid plasma bursts, offering blueprints for earthbound innovations in sustainable manufacturing. This isn't abstract science. It's a call to our collective soul. China's sharing of over 125 grams of samples has ignited global collaboration, with foreign scientists now probing these enigmas, publishing breakthroughs that unite us under the same starry sky. As we eye Artemis missions and international lunar stations, these discoveries fuel dreams of self-sustaining outposts, extracting water from scant mantle traces, forging graphene shields against radiation, turning moon dirt into bricks for habitats. Feel the urgency? The moon isn't waiting, it's evolving our understanding, pulling us toward a future where humanity doesn't just visit, but thrives among the craters. Let's grasp this cosmic hand, for in its grains lie the seeds of our interstellar destiny, blooming brighter with every revelation.